Hello everyone, this is chapter 1, second class. So in our previous video, we have explained um, until what data manipulation and language is DML. Now we are moving on to the SQL query language. So SQL is a widely used query language that is non-procedural, meaning it focuses on the what rather than how. Let's explore how SQL works and its integration with application programs. So non-procedural nature of SQL. In SQL, a query takes one or more tables as inputs and always returns a single table as an output. This non-procedural nature means that users specify the desired result without needing to outline the specific steps to achieve it. Example query, to find all instructors in the com science department, that is computer science department, you can use the following SQL. Select name from instructor where department name equals to computer science or com science. This query retrieves the names of all instructors whose department is computer science. The SQL has some limitations. SQL is not Turing complete, means it cannot perform all types of computation by itself. For complex processing, SQL is usually embedded within a higher level programming language. How does SQL access database? Application programs typically across databases through embedded SQL. SQL code is embedded within a host programming language, allowing for complex questions and control structures. And another one is APIs or application program interfaces. Interfaces like OBDC, like Open Database Connectivity, or JDBC, Java Database Connectivity, enable applications to send SQL queries to a database. By integrating SQL with a higher level programming language using APIs, developers can perform more complex data processing and build robust applications. SQL is a non-procedural query language. This is designed to specify what data you need rather than how to retrieve it. While this makes SQL very user-friendly and efficient for database queries, it has some limitations. So this is not Turing complete. SQL is not as powerful as the universal Turing machine. It lacks the capability to perform all types of computations. Limited action support. SQL does not handle actions such as user input, output to displays, or communication over a network. These types of operations are essential for building interactive and dynamic applications. So what is the role of a host language? To overcome this limitation, SQL is often embedded in a host language like C or C++, Java, or Python. These languages can handle complex computations and perform the input and output operation that SQL cannot. By embedding SQL within these host languages, developers can execute SQL queries to interact with the database, while the host language manages the application's overall logic and user implementation. Application programs are software tools that use embedded SQL within a host language to interact with a database. They handle tasks like taking input from users, processing data, and displaying the results. These programs provide a complete interface for users to work with the database, combining the data retrieval power of SQL with the versatility capabilities of programming languages. In summary, while SQL excels at data querying, it relies on integration with more comprehensive programming languages to build robust and interactive operations. Designing a database involves careful planning to ensure it meets both business requirements and technical constraints. The design process can be divided into two main phases: logical design and physical design. The logical design, this phase involves deciding on the database schema, which defines how the data is logically organized and related. So key decisions like business decision identify what attributes or data fields are important to record in the database. For example, in a customer database, we might decide to record attributes like customer name, customer's address, and purchase history. And computer science decisions. Determine the optimal way to organize these attributes into relation schema, like tables. This involves deciding what tables to create and how to distribute the attributes among these tables to ensure data integrity, minimizing redundancy, and improving query performance. Now let's talk about the physical design. This phase focuses on deciding the physical layout of the database. It involves how data will be stored, retrieved, and optimized for performance on the storage medium. The key consideration is storage structures, indexing methods, and data access paths are chosen to ensure that the database can handle the expected workload efficiently. Optimization of disk space and retrieval speed based on the specific requirements of the database application is also a key consideration here. The database system is a complex piece of software designed to manage large amounts of data efficiently. To handle its various tasks, a database system is divided into different modules, each responsible for a specific function. Let's look at the main functional components of a database system. Number one is the storage manager. The storage manager is responsible for storing, retrieving, and updating the data in the database. It manages the way data is stored on physical storage devices like hard drives or SSDs. So the functionality of the storage manager is managing data structures and accessing methods to optimize data storage and retrieval, handles file organization, buffering, and memory management, ensures data is stored securely and efficiently, balancing performance and storage requirements. Number two is query processor component. The query processor interprets and executes database queries. It converts high-level queries like those written in SQL into low-level instructions that the storage manager can execute. The functionality of query processor component is parsing, validating, and optimizing queries to ensure efficient execution, translates queries into execution plans and coordinates the retrieval and manipulation of data, and provides an interface for users to interact with the database using query languages. Lastly, let's look at the transaction management component. The transaction management component ensures that all database transactions are processed reliably and adhere to the ACID properties. ACID stands for atomicity, consistency, isolation, and durability. We will look into these ACID properties in details in our next classes. So it manages an execution of multiple transactions simultaneously while maintaining data integrity, handles transactions control, concurrency control, and recovery in case of system failures, ensures that each transaction is completed fully or not at all, protecting against data corruption. The storage manager is a crucial part of the database system, acting as a bridge between the low-level data stored in the database and the high-level application programs and queries. Let's explore the role of responsibilities of the storage manager in more detail. Role of the storage manager. The storage manager provides the interface between the physical storage of the data and the logical view of the data as seen by the application programs and queries. It ensures that the data is efficiently stored, retrieved, and updated, making sure that the operations of the database are handled smoothly and effectively. Responsibilities of the storage manager: interaction with the OS file manager or operating system file manager. It works closely with the open operating system's file management system to handle the physical storage of database files. And efficient data management. The storage manager is responsible for efficiently storing, retrieving, and updating data. This includes organizing data in a way that minimizes retrieval time and maximizes performance. Finally, components of the storage manager: authorization and integrity manager. This component ensures that only authorized users can access or modify the data and that all data modifications comply with the integrity constraints set by the data schema. Transaction manager manages transactions to ensure that the database remains consistent even in the presence of multiple concurrent transactions and system failures. The file manager is responsible for allocating the space on disk storage for database files. It handles the creation, deletion, and organization of these files. Finally, the buffer manager manages the buffer pool, which is a reserved area of the main memory that stores frequently accessed data. This helps in reducing the number of disk accessing and improving the performance of the database. The storage manager is responsible for implementing several critical data structures that are essential for physical system implementation for a database. Let's look at this key data structure and their roles. Number one is data files. Data files are actual files where the database's data is stored. These files hold all the record and data entities that make up the database. Data file, they serve the primary storage for all data, including table, rows, and columns. The storage manager ensures that these files are organized efficiently for quick retrieval and storage operations. Data dictionary. The data dictionary, also known as system catalog, stores metadata about the database. Metadata is essentially data about data, which describes the structure and organization of the database. It contains information about the database schema, such as the definition of the tables, columns, data types, and relationships. The data dictionary is crucial for the database management system to understand how data is structured and to enforce integrity constraints. Indices are data structures that provide fast access to data items in the database. They are similar to indexes in a book, helping to quickly locate specific information. Indices create pointers to data items and hold a particular value, enabling efficient searching and retrieval. For example, an index of a column containing customer IDs allows the database to quickly find records associated with the specific ID, greatly speeding up query processing. The query processor is a critical part of the database system, responsible for interpreting and executing queries. It consists of several components, each with a specific role in handling queries efficiently. Let's take a closer look at these components. DDL interpreter, or data definition language interpreter, processes DDL statements, which are used to define the database schema. It interprets these DDL statements and records the definition of the data dictionary. This ensures that the database structure, such as tables and relationships, is correctly defined and stored. DML compiler, or data manipulation language compiler, translates DML statements which are used to manipulate data into an evaluation plan. It takes high-level DML statements and converts them into a series of low-level instructions that the query evaluation engine can execute. One of its key functions is query optimization, selecting the most efficient evaluation plan from the various alternatives to minimize the cost of query execution. This involves choosing the best way to access the data, using indices and determining the order of operations. Finally, the query evaluation engine. The query evaluation engine is a component that actually executes the low-level instruction generated by the DML compiler. It carries out the evaluation plan, interacting with the storage manager to access and manipulate the data as specified by the query. The engine ensures that the results are retrieved and presented as required by the user's query. Query processing. In this slide, we look at the key stages involved in query processing. Within a database system, these stages ensure that users' query are efficiently translated into actionable commands and executed to retrieve or manipulate data. The process consists of three main stages: parsing and translation, optimization, and evaluation. Parsing and translation. This is the first step where the query is analyzed and converted into a form that the system can understand. The query is passed to the parser and translator. The parser checks the syntax of the query to ensure it is correctly formatted. The query is then translated into a relational algebra expression, which is an internal representation that describes the operation needed to fulfill the query. Optimization. Once the query is translated, it goes through optimization to improve its efficiency. The relational algebra expression is passed to the optimizer. The optimizer generates various possible execution plans, which are different ways to perform the query. It evaluates these plans based on cost, such as the amount of time or resources required. The optimizer selects the lowest cost execution plan to ensure the query runs as efficiently as possible. Evaluation. In the final stage, the selected execution plan is carried out to get the desired results. The execution plan is passed to the evaluation engine. The engine executes the plan by interacting with the database storage, retrieving, and processing of the data as specified. The result of the query is then produced and returned as query output. Transactions are fundamental concepts in database systems, ensuring that all operations maintain data integrity and consistency. Let's explore what transactions are and how database systems manages them. A transaction is a collection of operations that together perform a single logical function within a database application. For example, transferring money from one bank account to another involves multiple operations. Debit from one account, credit to another, but is considered one transaction. Transaction ensures that either all operations are completed successfully or none at all. This is all or nothing approach, prevents partial updates that could lead to data inconsistencies. Transaction management components. The transaction management component is responsible for ensuring that the database remains in a consistent state even in the event of system failure, such as power outages or software crashes. It enforces the ACID properties. ACID is basically atomicity, consistency, isolation, and durability. So it enforces the ACID properties to maintain database integrity. It handles transaction failures by rolling back the incomplete transactions to their previous consistent state, ensuring no partial changes are left in the database. Concurrency Control Manager. The concurrency control manager ensures that multiple transactions can occur simultaneously without causing inconsistencies in the database. It manages the interactions among the concurrent transactions, making sure that operations do not interfere with each other. For example, if two transactions are trying to update the same data at the same time, the concurrency control manager coordinates these updates to avoid conflicts. This management is crucial for maintaining the isolation property of transactions, ensuring that each transaction is processed as if it is the only transaction running at that time. Database architecture refers to the design and structure of the database system, determining how data is stored, managed, and accessed. Let's explore different types of database architecture commonly used. Centralized databases. In centralized database architecture, all the data is stored and managed in one single system, often within one to a few cores and shared memory. All database operations are performed on this central system. It simplifies management and data control, but can become a bottleneck as the demand increases. A small business using a single server for all its data storage and processing needs is an example of centralized database. Client server architecture. In this model, a central server handles requests from multiple client machines. There is a server, a powerful machine that executes database operations and manages data storage. Clients, user machines that send requests to the server for data processing and retrieval. This architecture allows for more scalable solutions as the number of clients can grow. An example is web application where user devices are clients requesting data from a central server. Parallel databases. These databases are designed to take advantage of multiple processors and cores to perform parallel processing of data. Many cores shared memory. Multiple processors share the same memory space, allowing the fast communication and data processing. Shared disk. Each processor has its own memory but shares a common disk. This setup allows for a better data redundancy and scalability. And shared nothing. Each processor has its own memory and disk. This architecture scales well because each unit operates independently, reducing bottlenecks. A use case is high performance applications that requires fast processing and large datasets like data analytics platform. And finally, distributed databases. In a distributed database, data is stored across multiple geographic locations with each site having its own database system. For example, geographical distribution. Data is distributed across various locations to improve access speed and redundancy. Or schema data heterogeneity. Different sites may use different database schemas or even different database management systems, requiring strategies to integrate and synchronize the data. This architecture provides high availability, fault tolerance, and better performance for global applications. Example is a multinational corporation with offices around the world where data needs to be localized but also accessible company-wide. This diagram provides an overview of the architecture of a database system, illustrating how different components interact to manage and process data efficiently. Let's break down the main components and their roles. The query processor. The query processor responsible for interpreting and executing user queries. It includes DML compiler and organizer, DDL interpreter, query evaluation engine. Then application program interface or APIs. The application program interacts with the database through an API using embedded SQL to send queries and commands. This interaction involves compiler and linkers. Then there is storage manager. The storage manager handles the efficient storage, retrieval, and updating the data. It comprises buffer manager, file manager, authorization and integrity manager, and transaction managers. And finally, disk storage. The actual data and the metadata are stored in the disk storage. Key components include data, indices, data dictionary, and statistical data. Database applications are typically organized into different layers or tiers to separate concerns and improve scalability and manageability. Let's look at the two most common types of architecture, two-tier and three-tier. The two-tier architecture. In two-tier architecture, the applications is split between the client and the server. So how does it work? The application logic resides on the client machine, which directly interacts with the database system located on the server. The client sends the request to the server to access or modify data, and the server processes this request and returns the results. The advantage is simplicity, easier to set up and manage, especially for smaller applications. Direct communication between client and the server can result in faster response times for single queries. So the use case for this is suitable for a small and medium-sized application such as desktop application or internal company tools. Now, three-tier architecture. In the three-tier architecture, introduce an additional layer known as the application server between the client and the database. So how does it work? The client layer, the client acts as a front end, often using forms interface of web browser. It does not directly call the database, but instead communicates with the application server. Application server layer, this middle layer contains the application logic and business rules. It processes requests from the client, performs any necessary computations or logic, and then interacts with the database system to retrieve or update data. Finally, the database layer. The database system stores and manages the data. It communicates with the application server to fulfill data requests. The advantage, scalability. The separation of layers allows the system to handle more clients and larger amounts of data by distributing the workload across different servers. Security. Clients do not have direct access to the database, reducing the risk of unauthorized access or malicious activities. And maintainability. Changes to the application logic can be made at the application server level without affecting the client or the database layer. This is the use case is like ideal for large scale web applications, e-commerce platforms, and enterprise system where scalability, security, and maintainability are critical. So this is just an example of the two-tier architecture and three-tier architecture. Here you can see user, application, and then the database. These are two different servers. This is the client server. This is the this is the client, and this is server. And here in the server we have application server. This is different from the database system. Application server talks to the database system, and application client talks to the application server, not directly to the database server. This diagram illustrates how different types of users interact with the database system and how the query processor handles these interactions. Let's break down the different user roles and the components involved in processing their request. Type of database users: naive users like tailors, agents, and web users. These users interact with the database through application interfaces. They perform routine operations like checking account balances, booking tickets, or browsing products. Then application programmers. They write application programs that interact with the database. These programs handle specific tasks and user needs, translating users' actions into database queries and updates. Sophisticated users or analysts. Analysts are and power users are users use query tools to interact directly with the database. They run complex queries to extract meaningful insights from the data, often using advanced analytics and reporting tools. And finally, the database administrators or the DBAs. DBAs are administration tools, use administration tools to manage the database. They define schemas, set up user permissions, and ensures data integrity and security. Interaction with the query processor. Application interface used by the naive users to interact with the database through a user-friendly interface. These interfaces send predefined queries to the database. Application programs written by application programmers. These programs are compiled and linked into executable codes that interacts with the databases. Query tools used by sophisticated users to construct and run complex queries directly. These tools communicate with the DML compiler and organizer to process data manipulation language or DML queries. And finally, administration tool. Utilized by the DBS, this tool interface with the DDL interpreter to manage the database schema and maintain database structure. Components of the query processor. Compiler and linker converts the application program code into executable form that can interact with the database. DML compiler and organizer translates DML queries into low-level instructions, optimizing query execution for efficient data retrieval and updates. Query evaluation engine executes the instructions generated by the DML compiler, performing the necessary operations on the data. And finally, DDL interpreter processes the data definition language or DDL statements to define or modify the database schema, storing these definitions in the data dictionary. In a database system, the DBA or database administrator plays a crucial role, having central control over the system. The DBA is responsible for a variety of tasks to ensure that the database runs smoothly and securely. Let's discuss the key functions of a DBA. Schema definition. So the DBA is responsible for defining the schema, which is the logical structure of the database. Storage structure and access method definition. The DBA defines how data is stored in the database, including choosing the appropriate storage structure, accessing methods to optimizing performance. Schema and physical organization modification. As requirements change, the DBA may need to modify the schema or the physical organization of the database. This could involve adding new tables, changing existing table structure, or reorganizing how data is stored. Granting of authorization for data access. The DBA controls access to the database by granting or revoking permissions. This ensures that only authorized users can access or modify data, maintaining security and data integrity. Routine maintenance. Routine maintenance tasks are critical to the health of the database. These tasks include periodically backing up the database, ensuring enough free disk space, and monitoring jobs running on the database. These are some history of the database systems. 1950s and early 1960s, data processing with magnetic tapes. During this era, data was primarily stored on a magnetic tapes, which provided only sequential access. This means data had to be processed in the order it was stored, making it difficult to retrieve specific information quickly. Punched cards for inputs were used, but late 1960s and 1970s, introduction of hard disks. The invention of hard disks marked a significant advantage, allowing for direct access of data. This made data retrieval much faster and more flexible. Network and hierarchical data models. These models were widely used, organizing data in tree-like structures that allowed for more complex data relationships. However, they are still somewhat rigid and difficult to modify. Relational data model by Tate Cod. Tate Cod defined the relational data model, which making it easier to understand and manipulate. Cod's work in the relational model earned him the prestigious ACM Turing Award. System R and Ignis prototype, IBM System R. IBM Research started developing the System R prototype, which implemented the relational model and laid the groundwork for SQL. And Ingres at UC Berkeley, Michael Stonebraker led the development of the Ingres prototype, another early implementation of the relational model that would influence many future database systems. And finally, Oracle's first commercial relational database. Oracle released the first commercial relational database, bringing the relational model into practical use in the business environment. This marked the beginning of high-performance transaction processing, a crucial feature for modern database applications. In 1980s, commercial relational systems like research prototypes like System R and Ingres evolved into commercial relational database systems. Companies began adopting relational database for their flexibility and efficiency. SQL became the standard. SQL emerged as the standard query language for relational database, solidifying its role in the data manipulation and retrieval. Parallel and distributed databases. Advances in technology led to the development of parallel and distributed database systems. Institutions like the University of Wisconsin, IBM, and Teradata pioneered these systems, enabling faster processing and data distribution across multiple machines. Object-oriented database. The concept of object-oriented database also emerged, aiming to integrate object-oriented programming features into database system to handle the more complex data types. And looking into 1990s, large decision support and data mining. With the growth of data volumes, there was a shift towards the large-scale decision support system and data mining applications, which help business analyze and extract insights from their data. Multi-terabyte data warehouses in 1990s saw the rise of large data warehouse capable of storing multi-terabyte data sets, and web commerce emergence. And the advent of the internet and the web commerce dramatically increased, and the demand for robust, scalable database system to handle online transaction, user data, and e-commerce activities. In the early 20s, big data storage system like Google, Bigtable, Yahoo, Peanuts, Amazon came. NoSQL system is a widely used system. The limitation of traditional relational databases handling unstructured data led to development of NoSQL system. So SQL only handles structured data. NoSQL can handle unstructured data as well. Big data analysis beyond NoSQL, traditional SQL-based processing was not sufficient for analyzing massive datasets, leading to new paradigm like MapReduce. This approach allows for distributed data processing across large clusters of machines. In the 2010s, SQL Reloaded. So despite the rise of NoSQL, SQL made a comeback as a front end for big data processing. Systems were developed that allowed SQL queries to be executed over big data. Frameworks like MapReduce, combining the familiarity of SQL with the scalability of big data solutions. Massively parallel distributed systems came on, and multi-core main memory databases also started emerging in this era. Advances in hardware technology, particularly multi-core processor and large main memory capabilities, led to the development of in-memory databases. So this is the end of chapter 1. Let's meet in our next videos. We will go over chapter 2 in the next weeks. Thank you.